Good morning. This morning I'd like to talk with you a little bit about integration by parts in a little bit different style. Um, Dr. Jan Zijlstra is a professor of mathematics at MTSU, Middle Tennessee State University, and the other day I was working with a student in the math lab on integration by parts, but they were working on integration by parts in a way that I was not familiar with. I was a little stumped. And so when I got a chance, I went and talked to Dr. Zijlstra because I know him to be a very good professor, and I figured he probably had a good reason for what he was doing, and he does. His method is pretty clever. And I was surprised to find that not only did it make me think about integration by parts in a different way, it made me think about integration in general in a different way. And so I'd like to share that with you this morning. In order to understand his method, it's important first to talk a little bit about integration in general. Let's take, for example, this integration. The integration, right? The integral of 1 with respect to x, right? What Dr. Zijlstra told me is that if you think about these as inverse operations, as the integral and the dx as being inverse operations, what do we know about inverse operations? Well, if you compose two inverse operations, your answer is x. And don't we know the integral with respect to x to be just x, right? So if we extend that a little bit further, let's talk about this information. What if we rewrite this as the integral with respect to sine x? Don't we know the integral of cosine x with respect to x to be sine x? Well, what if we just kind of cut out the middleman a little bit, or maybe even put the middleman back in, I suppose, and called it the integral with respect to sine x? Well, then it makes sense that these two inverse operations would cancel out and leave us with just the sine of x. And it's this idea, this moving, this fluidity of integrals and differentiation within the integral notation that makes this new integration by parts possible. So let's take it back the other way. If the integral of cosine of x dx is the integral with respect to sine x, what we've done here is we have just integrated to get this notation changed. If we want to go back the other way, we can move things back in front of the dx, so to speak, by differentiating. I'm not going to write out differentiate because it's a really long word, but we would end up with this. Okay, and that leaves our dx back there as just a placeholder. So now it's just with respect to x. So let's take this a little further and let's look at an actual integral in terms of this kind of integration. Suppose we have the integral of x sine x with respect to x. Well, using integration by parts, I would choose a u and a dv and all that kind of stuff to make this happen. In fact, let's write that rule down here at the bottom. So we know that the integral of u dv is u times v minus the integral of v du. That's the rule, right, for integration by parts. So if we go back up and look at what we have here, instead of over to the side assigning a u and a dv and doing the work, what if we did this? What if we simply differentiated, or excuse me, integrated inside so that we end up with negative cosine of x. So this is negative integral of x with respect to cosine x. Now we have just chosen our u and our dv. Do you see that? So let's write our rule out. So this should be equal to u times v minus the integral v du. Let's see what happens when we put this information back in. So this is negative u times v minus the integral of v du. And isn't that lovely? I know what the integral of cosine is. That is fabulous. So I end up with negative x cosine x plus, and the integral of cosine is just simply sine plus a constant. And that's really nice. It's really pleasant not to have all this u and dv business out to the right-hand side. And you might be saying to yourself, that's kind of a nice trick, but what's the point? Where's the real advantage here? And I can see your point. So let's take it a little further. What if we had this? Now that's kind of sticky. In traditional integration by parts, if we chose a u and a dv, it wouldn't really matter which one we choose because the integral of e to the x is e to the x, and the derivative of e to the x is e to the x. So it doesn't change. It just keeps going round and around and around, and it just never gets any simpler, never gets any more complex. Cosine of x does the same thing. If we take the derivative of it, we get negative sine x. If we take the integral of it, we get positive sine x, and it doesn't get any more complex or any more simple. So, I mean, I guess you could say a negative makes it somewhat more complex, but we're in Calc 2 now. The negatives are negatives, big deal. So instead, what Dr. Zijlstra would have us do is to look at one or the other of them. It doesn't really matter. So I'm going to use e to the x, and I'm going to move it. We're going to just call this behind the d. It's probably not the technical term for it. But if we take this cosine of x with respect to e to the x, we have now, again, just chosen our u, d, v. And so if I execute the integration by parts rule, I have u times v minus the integral of v d u. Now, we didn't have this before, this like d cosine x business. On the last one, it was quite simple. We just ended up with dx. But now we have something a little bit more complex. So let's just take it back and really analyze what we have. Let's take it back by differentiating, right? Take the derivative with respect to x of cosine of x. And we end up with this. I'm going to rewrite this because we're used to seeing it e to the x cosine x minus e to the x times, well, the derivative of cosine is sine. Actually, it's negative sine, so let's change our sign there. It's a lot of signing. All right, with respect to x. Now, this is not any simpler or any more complex than what we started out with. In fact, it's just as fussy as what we started with. So let's do it again. We know that in some integration by parts problems, we have to just do it again. So I'm going to be consistent and take this same guy and integrate so that I have e to the x cosine x. It's annoying to have to write out this e to the x cosine x about 5,000 times, but we're going to have to, so we do. Sine x with respect to e to the x. And now again, we've chosen our u and our dv. So we go back, e to the x cosine x plus u times v minus the integral of v du. And again, I'm going to take it back. I'm going to differentiate again. Does anybody see what's about to happen here? Of course, you can't answer me because this is a video. Plus e to the x sine x minus the integral e to the x. The derivative of sine is cosine without a sign change. And look what I've got. I've got precisely what I started with, which is either annoying or really a relief, depending on your point of view. This guy right here is the same as this guy right here. That's the very same thing we started with. So let's push the paper up a little bit, And let's rewrite the problem. If I rewrite the problem, I'm starting in a new color so that we can see that we're just rewriting. The integral of e to the x cosine x with respect to x is equal to, thus far, e to the x cosine x plus e to the x sine x minus the integral of e to the x cosine x with respect to x. And so if I just simply do a little algebra, I've got the answer to this problem. If I add the integral e to the x cosine x with respect to x to both sides, then when I stack it up here, when I do a little simple algebra, stuff we learned back in Algebra 1, I've got twice the integral of e to the x cosine x dx is equal to e to the x cosine x plus e to the x sine x. I'll go ahead and put our constant in, plus a constant. And so all I have to do now is just multiply both sides by a half, and I've got it. So now I know that the final answer is that e to the x, the integral of e to the x cosine of x with respect to x is half e to the x cosine x plus e to the x sine x plus a constant. By the way, why does it not matter where I put that constant? Because a constant is just a number. And so it could have been something divided by 2. It could have been something times 2. It doesn't really matter. And since it's a constant, it'll absorb that 1/2, and I don't have to worry about putting it inside the parentheses or saying it's 1/2 the constant or whatever. Okay. Since they haven't given us any bounds, any definition information about it, we can't decide what that constant is anyway. So here's our final answer. We started, so this full process took us through integration by parts once and then again, but we don't have over to the side any of this u equals whatever, dv equals whatever, right? We don't have to write that over and over again. That is unnecessary. And so we have a nice clean integral in which we have used a very fluid method for integration by parts in order to get to the final answer. And many of you have probably experienced this in the past, but I want to point this out. And that is that this guy right here, because we had to write him over and over and over and over and over again, some students get really frustrated in that process and just stop writing that term. That's a mistake. Don't do that. It's tedious, it's irritating, but if you will keep all of your algebra together and not drop off bits of it, hoping that you'll remember to pick them back up again later in the answer, you'll be much more likely to get to the right answer, to arrive at the correct answer. So anyway, so that's integration by parts using Dr. Zijlstra's methods. On this first slide here, I put up my personal information. My name is Melody Elrod, and I am a grad student currently at MTSU, but I'm also a private tutor in the state of Tennessee. I also tutor online. So if this is helpful to you and you'd like to talk to me more about how I could be helpful to you in the future, feel free to visit melodyelrod.com, and you will find a wealth of contact information there. And hopefully this has been helpful to you, and I hope you have a great day. Thanks.